Hi, welcome to our new unit, which is KMT. That stands for Kinetic Molecular Theory. And what this is a theory of how particles move. Kinetic energy is the energy of motion. So here we have our chart on our solids, liquids, and gases. We did a quick overview of this in Unit 1, and we're going to talk about it a little more in more detail for this unit. So first of all, we talk about the spaces between particles. Our solids are very tightly packed and they're orderly. Our liquids are also very tightly packed. Now, it looks like there's some spaces between here, but it turns out there's really not much space here. It just looks like that because they are disorderly, so they're not ordered in straight lines like these solids or in a crystal lattice. Our gases have lots of space between them, and they are disorderly. Now, because of these spaces, we can not compress solids. There is no space to get these molecules any closer, and it turns out we can't compress liquids either. But our gases is full of all these empty spaces, so we can squish these gas molecules to where they're touching so we can compress that. That's why we have aerosols, which are compressed gases, or if you went to fill up some party balloons with helium, helium is compressed into a little, you guys can buy one of those little balls of helium, and they'll fill like 400 balloons. That would be a lot more space. So the gas is compressed, we release it, and then it takes up some more volume. The movement. So this solid table seems like it's not moving, but everything on Earth is moving unless it can hit absolute zero, which we haven't done yet. And so all of our solids are vibrating. They're just vibrating so small that you can't even notice those vibrational motions for the most part. Our liquids are slipping by each other. So they are in movement, and these gases are moving like crazy. And if you move your hand around back and forth, you can actually feel those gas particles hitting your hand. And so they're just bouncing around. So energy. Well, if you were sitting on a couch and you were barely moving, you'd have very low energy. Or if you were bouncing off the walls like gas molecules, we would say that you had high energy. So we go from low energy to high energy, okay? Forces of attraction. When we're well, let's go back here. Our comparative energy, we're talking about kinetic energy, which is the energy of motion. So let's make sure we write that down. Our forces of attraction between particles. We've already learned about those. What brings two water molecules together? Well, those are intermolecular forces. And we can see we have very strong intermolecular forces in solids. They're very tightly packed and attracted to each other. And then over here in gases, they're not attracted to each other at all. We're going to say they have no intermolecular forces. Real gases do have just a little bit of intermolecular forces, but it's not noticeable unless we have very high pressure or very low temperature. So for our class, we're going to say there's no intermolecular forces in gases. Density, how much stuff can you fit in the same box? I can fit a lot of molecules if they're packed very tightly. So this is very dense. Over here, these guys have a lot of space between them. So there's very few molecules in the same amount of space, which makes that our least dense of these three phases: solid, liquids, and gases, these three states of matter. Okay. So now shape and volume. We have very particular words we use to explain if the shape changes. So here I have a solid eraser. I put it in a container. Did my eraser change shape? It did not. It is a solid. So solids have a definite shape. Oops. And they also did not change the amount of space it takes up. That's our volume. So we have a definite volume. Now over here, when we talk about gases, if I let a gas out of container, it would fill the whole room. So you could think of like perfume. If I open a perfume bottle, that liquid turns into gas, and after a couple of minutes, you'd smell it in the whole room because the gas filled the room. So it changed the volume, and we call that an indefinite volume. And that just means it's changeable. Okay, now it also filled the whole shape of the room. You can smell the perfume in every corner, so it's an indefinite shape. And water is split between those. So here I have a graduated cylinder, and if I froze this water, it would be in the shape of a cylinder or a column. Now I can pour this water into a cup, and now instead of being a cylinder, I have basically a hockey puck down there. So it has an indefinite shape for a liquid. It changes the shape to fit the container, but I had 10 mils of water, and when I pour it in the glass, I still have 10 mils of water, so we have a definite volume, okay? So why do gases have the most energy? Well, we're talking about kinetic energy, so we want to say they have the most motion of all our states of matter, okay? So we want to keep going and describe our states of matter, but before we do that, we have a few vocab words. We have kinetic energy, which we already said was the energy of motion. Then we have temperature. And then we have our temperature, and this is the measure of the average kinetic energy, and we use a thermometer to figure this out. Now, if I put a thermometer in a liquid, I'm going to get like, let's say 74 degrees. And that's basically how fast these molecules are moving. But it's the average kinetic energy, so not all of the molecules are moving at the exact speed. Some of them are moving slower, and some of them are moving so fast that they can escape the attractions and they could evaporate. So when we talk about temperature, it's the average kinetic energy. Now, I moved this endothermic up here. That may have already been done on your packet. If not, move it up here. And thermic is, we're talking about heat energy. And we could add energy to a system, or we could have heat being removed from the system, or it's escaping or leaving the system and going into the surroundings. So what we want to do is look at our two prefixes. Exiting means heat is leaving. Okay, so exothermic is heat is leaving, and endothermic means heat is entering. Okay, or it's being added to the system. Now, what we have here is a solid, liquid, and gas. For me to go from a solid to a liquid, these guys are moving faster, so I need to add energy to that. So if I add energy, it's endothermic, going from a solid to a liquid to gas, and here I'm removing energy, so going this way, it's exothermic. So as these guys slow down, they're giving off heat, they're giving off that energy. They don't have as much at the end, so it's going into the surroundings. It's exiting that system, so it's exothermic. And now we have our states of matter. And what I like to tell my students is that if you think about water, you're going to get most of these states down. Okay, so if a liquid goes from, or if water goes from a solid to a liquid, it's melting. And if it's going from a liquid to a solid, it's freezing. If I take a liquid and it evaporates or boils, so it's going from a liquid to a gas, we're turning it into water vapor. So we're going to call this vaporization. And if that gas turns into a liquid, I want you to think about your glass on a hot summer day and it has ice in it. What forms on the outside of that glass? Well, what forms on that outside of the glass is condensation. And I get a lot of funny answers about where that condensation comes from. A lot of people say it comes from inside the glass. Well, I'm here to tell you that water cannot go through glass, so it's not coming from there. But our air is full of water vapor, and that's what we call humidity. And when that water vapor hits our cold glass, it slows down those molecules and it turns into a liquid, and that's the condensation on the outside of your glass. Now we can bypass going from a solid to a liquid to a gas or gas to a liquid to a solid, and we can go from a gas right to a solid, and that is called deposition. And that is like frost on your grass in the morning. We have that solid frost if it's very cold. Well, that came from the humidity, that gaseous water in our air, and it formed that solid on our grass. Vice versa, if we go from solid right to gas, that's called sublimation. And that is like dry ice. So they use dry ice and it goes right to a gas, and that's how they make fog on stages for concerts and things like that. That's very helpful because if I took regular ice and melted it on the stage, we'd have a slip and slide going on. So they take that dry ice, it forms that water gas, and it looks like fog when we have those concerts. When we do our vocab, I want you to know our vocab is going to be very easy. Remember, I want you to write it in the least amount of words that is understandable to you so we can get that vocab down. So condensation is when we go from a gas to a liquid. Freezing is when we go from a liquid to a solid. Melting, we're going from a solid to a liquid. And sublimation is when we go from that solid to a gas. If we turn things into vapor, we're taking liquids and turning them into gas. So evaporation, boiling, normal boiling point pressure, that's going to be our next video.